Welcome to this explainer. I am absolutely thrilled you're here today because we're going to expose the hidden, invisible mechanics that literally hold our physical world together. We're taking a deep dive into the realm of electrostatics. And it's a field of physics that sounds incredibly complex on paper, but as you'll soon discover, it governs things you interact with every single day. To get us started, I want you to picture a classic, totally relatable everyday mystery. Have you ever run a plastic comb through your dry hair, brought it near some tiny torn-up pieces of paper on a desk, and just watched as those pieces magically leap up and stick to the comb? I mean, it looks like gravity has just been temporarily switched off. And what's even weirder is that sometimes, right after they touch the comb, they suddenly shoot away from it. No way, right? Why does this happen? Well, stick with me, because by the end of this explainer, you're going to know exactly how this invisible magic trick actually works.
Okay, let's dive into this. Here is our agenda for today. 1. The basics of electric charge. 2. Electrification, or moving the electrons. 3. The magic of electrostatic induction. And finally, 4. Real-world electrostatic applications.
Starting off with Section 1, the basics of electric charge, the foundational rules of the invisible. To truly understand the macroscopic world, things like our comb and the paper, we first have to zoom way down to the subatomic level. Electric charge is formally defined as the physical property of matter that causes it to experience a force when placed in an electromagnetic field. Now, that force can be an attraction pulling things together or a repulsion pushing them apart. It's absolutely crucial to understand that charge isn't just some random event or fluke, it is a fundamental, built-in property of the substance itself. And in the world of physics, we measure this property in a unit called coulombs, which is just represented by a capital C. Now, things get really fascinating when we look at the two types of charge. You've got your positive charge and your negative charge. But what actually dictates this? Well, it all comes down to electrons. I want you to think of electrons like tiny, restless nomads. They are the particles that easily transfer between objects. So an object gets a positive charge if it has fewer electrons than normal, meaning it has a deficit. Conversely, it gets a negative charge if it has more electrons than normal, an excess. The entire positive or negative identity of any object is based entirely on the movement of these mobile little electron nomads.
Moving on to Section 2, Electrification, how objects become charged.
Since charge is all about a surplus or deficit of electrons, we need to figure out how these charges actually transfer to create those imbalances in the first place. Check out the top diagrams here showing how early physics experiments proved this. If you rub a glass rod with a silk cloth, it becomes positively charged. If you suspend that glass rod and bring another positively charged glass rod near it, they literally twist away from each other. The exact same thing happens with rubber rods rubbed with animal fur, which become negatively charged. When you bring two of those negative rubber rods together, they push apart. This proves a universal ironclad rule. Identical or like charges will always repel each other.
So the crucial point here is that when we rub silk on glass or fur on rubber, we aren't just summoning electric charge out of thin air. Electrification is strictly the transfer of electrons. The friction between those two different materials simply rips existing electrons from one and deposits them right onto the other. Charge is never created, it's never destroyed, it is only ever moved around.
But what happens when we mix our rods? Take a look at the diagram at the top. When we take that positively charged glass rod and bring it near the negatively charged rubber rod, the exact opposite happens. Instead of twisting away, the suspended rod swings right toward the other one. They are powerfully drawn to one another. And this gives us the second half of our foundational bedrock rule of electrostatics. While like charges repel, opposite charges always attract.
Section 3, the magic of electrostatic induction, influence without physical contact.
Okay, so we know rubbing things together transfers electrons through direct contact, right? But here is where it gets crazy. These invisible forces can actually act over a distance without any physical touching whatsoever. This phenomenon is called electrostatic induction. It's defined as a change in the distribution of electrical charge in an object caused by the influence of nearby charges. I want to heavily stress those two words, distribution and nearby. The object itself isn't gaining or losing electrons to something else. Its internal electrons are just rearranging themselves because they sense a charge close by. No physical contact is required at all.
Let's walk through exactly how this works step by step so you can really mentally map this invisible electron movement. Step 1. Imagine two totally neutral metal spheres touching each other.
We bring a negatively charged rubber strip very close to them, but we do not let it touch. Step 2. Because we know like charges repel, the free electrons inside those metal spheres desperately want to get away from that negative strip. They are repelled all the way to the far side of the second sphere. Step 3. While holding that negative strip firmly in place, keeping those electrons pinned to the far side, we physically pull the two metal spheres apart.
And this brilliantly illustrates the magic of induction. Notice in the bottom diagram how, because we separated sphere X and sphere Y before removing the rubber strip, the electrons couldn't flow back to balance things out. Sphere X is now trapped with the deficit of electrons, making it permanently positive. Sphere Y is trapped with an excess, making it permanently negative. We successfully charged both of those spheres without ever actually touching them with our original charge strip. How cool is that?
And with that piece of the puzzle, we can finally solve our comb mystery from the beginning. When you bring a statically charged comb near those tiny pieces of neutral paper, the comb induces an opposite charge on the surface of the paper closest to it. Opposites attract, so the paper leaps up to the comb. But here is the twist. Once they physically touch, actual contact electrification happens. Electrons transfer between them until they share the exact same charge. And because like charges repel, the electrostatic force suddenly reverses, violently pushing the paper away. It's induction first, followed immediately by contact electrification.
Finally, Section 4, Real-World Electrostatic Applications. Harnessing the invisible forces.
Now that we really understand the atomic mechanics of this, let's scale things way up and see how humans and nature itself utilize these exact same invisible principles. Contrast human engineering on the left with nature's ultimate engine on the right. In coal power stations, we use things called electrostatic precipitators. Smoke passes through a positively charged grid, which gives the dust particles a positive charge. They are then instantly attracted to negatively charged plates on the chimney walls, literally pulling the pollution right out of the air. Over on the right, nature does this exact same thing inside a thundercloud. The bottom of the cloud becomes heavily negative, which, via induction, pushes electrons away in the earth below, creating a highly positive ground. When that attraction becomes just too strong, the air breaks down and a massive spark leaps between them. We call it lightning.
Let's also see how this translates into everyday manufacturing like painting cars. In electrostatic spray painting, the spray gun actually gives the paint droplets a negative charge, while the car itself is grounded and positively charged. As the paint leaves the gun, it acts like a homing missile. It is magnetically drawn directly to the metal surface. And because all the paint droplets share the same negative charge, they actually repel each other midair, creating a perfectly uniform fine mist. This means it wraps around difficult angles, creates a much stronger bond, and vastly reduces wasted paint, which is great for the environment. It is a wonderfully elegant, real-world application of opposites attract and likes repel. So we've gone from rubbing rods with fur to floating pieces of paper, all the way up to industrial smokestacks and raging thunderstorms. The rules of the universe remain consistent no matter the scale. Now that you understand the hidden power of these traveling electrons, I want to leave you with this thought. What other invisible forces are constantly shaping the physical world around you, hiding right there in plain sight? Keep observing, keep questioning, and thank you so much for joining me for this explainer.